Okay, this is tape number 3, still phase noise measurements, but this particular presentation deals with the single oscillator technique for measuring phase noise. It's a very good technique to have, and with all the the perfections they've made here, and especially the ones that are contributed by Fred LeBar, make it possible to make measurements very close to the carrier, and something we could not do in our original system. Now basically, the delay line discriminator, and by discriminator you mean it's a system that discriminates frequency-wise. It's a frequency discriminator. So now instead of measuring phase with a phase detector, we are going to be measuring with a frequency change by delay line discriminator. We're going to take the signal, split it, send this through the unit where we can get the 90-degree phase quadrature of the signals into the mixer over here. We're going to delay this signal in this line so that the signals now, the noise is decorrelated. If these were equal line lengths, you couldn't measure because it's a correlated signal. So you put a long delay line in here. By the time that signal gets here, it's changed. It looks like you've had frequency changes of these signals. So it's a decorrelated type of signal now. Now the length of this delay line, you'll see how it corresponds to particular frequencies it measured, and the offset frequency or the Fourier frequency that you perform measurements at. This is essentially what you're going to do. You're going to delay this. Now you have to calibrate this as a frequency discriminator, which means you have to know the output over here in terms of volts per hertz. And we'll do that calibration by deliberately that's at number 2 tape. Could you shut that? I wonder if it'll work for the next one. Well, let me turn it to the next one and see if it'll make the next one. That's good enough. Let's go from there, right? Ready to go?
Yeah, we're all.
Okay. Sorry for the disruption, but that's the problem with the slides. This is basically the system then where you have a cavity in this area here, and you can see all you're going to do is calibrate for the slope of the discriminator, whatever it's a delay line or whether it's a cavity. These equations you see on here in terms of the Q of the system. The signal coming in here, we're going to make the measurements over here. And I'll go to other slides to show that because that's a slide that doesn't belong to me. Here's the way this system worked when Ashley used it. He brought a signal in here into a circulator, out through here to a short circuit, back through here. So this line is half as long as the line we would put in line like this. This signal, of course, goes into the mixer. So here you have it. Signal goes through a phase shifter to set quadrature of the signals here. This goes through a long delay line to decorrelate the signal and make it so you can see the phase noise. Then these measurements of phase noise are going to be measured. You're going to calibrate this to get the sensitivity in volts per hertz of this frequency discriminator at this point. Then the rest of this is exactly the way we had this in the other system. Make the same type of measurements, but the calculations will be different because the calibration now is in terms of the frequency calibration at this point. So how are you going to do that? Well, you're going to have to intentionally modulate this source here in order to calibrate this at this point. So you're going to use intentional modulation. We'll show you how you do that because we have a system. Here's what the delay line looks like. Here's a delay line of cable here down around the 2GC area, and the system for I just vary signal, but anyway, here's the delay line, what it looks like. This thing right here is for setting this is the phase shifter for that one arm. The phase shifter is just a trombone. You got Neil up there and Frank up there. They were doing the original work. Well, let's look at the system then. Here is a source. If you have a source that cannot be modulated, you have to set up your levels in the system and know what they are. Then you take a source and set the same level, same frequency in here. Then you modulate this with a modulatable signal generator, In other words, you put this modulatable signal generator here. And on this spectrum analyzer, you look at the display. Let's see if I can't make it all of it. I get this one clean and this one's blurred. But anyway, you put this here and you modulate this, say for the first decile null, 2.4 essentially, you know. So you'll have set the modulation frequency and set for the modulation index of 2.4, and I'll show you the mathematics in a few moments of how this is done. So you modulate that, and you look at the spectrum analyzer, you see, and you adjust the modulation so that you get to the first decile null. Then you know the modulation index. And since you've intentionally modulated it, now you know that you can perform a measurement, which we'll do a little later, and get the calibration. That's going to be the calibration of this delay line discriminator and be calibrated so you know it coming out here. You have so many volts per hertz. Then we'll look at the equations. All the rest of this is just attenuators and isolators and DC blocks for the system. But here's your delay line portion here. You saw that for this we had that trombone in the system we just looked at. We have for setting levels of attenuator. Delay line over here. The DC scope, again, you put this so that you have here a line, just a straight line on this scope representing DC. Into a low-pass filter, an attenuator in the system. This is the attenuator you set to high values of attenuation when you're performing the calibration. Now let's look at this then in the system. The calibration factor, you're going to get a variation of the voltage by intentional modulation, and you're going to measure the voltage. Now, the way you do this, then, is you have the calibration factor is the modulation index times F sub m, the modulation frequency, divided by the square root of 2 times the VRMS. Okay? Now, when you look at that, in our case, we said we'll modulate this to first decile null, 2.405 times F sub m, square root of 2 times VRMS. Now, how do you get VRMS? That's the RMS voltage that you're reading at the output in the system. Well, you're going to measure it with a spectrum analyzer. When you measure it with a spectrum analyzer, you measure P, the power, in dBm. Okay, now you have a 50 dB attenuator in there too, you know. But you're going to measure this power in dBm here. So you're going to have to make corrections for it. So you're going to have 10 to the P in dBm divided by 10. This 1,000 changes this from dBm to watts, because watts you use to get the volts, times 500, and that's going to give you this VRMS. That's the output voltage that you measure, because you see, remember in our other system we measured power in dBm? In this case you have to measure power in dBm, but you convert that to voltage, and you use that in these equations here in our program. And this then is the calibration factor. This whole equation here, hertz per volt. So now you have a calibration factor in hertz per volts. That's the value they call K sub D, that the Hewlett-Packard calls K sub D. All right, now that's the way it's done then. You measure the noise power, dBm, correct for the attenuator setting. So then you have this value for the actual value, VRMS. Now that's measured, you know, straight through by modulating and looking at the signal in the spectrum analyzer and measuring it. Now, when you have a delay line, if I had a delay line this long, okay, suppose I have both channels of a system the same length. As I sweep them in frequency, what would you see? Just a straight output of that signal, output of the mixer, if you had a mixer on the other side. You'd see just a constant one signal out. So you have two channels with a mixer over here. So you sweep the signals in both channels. You get no phase shift between the two, and you would get just a straight line output. Now, if I increase the length of one side and start in and sweep the frequency, if I start at 0 frequency, when I sweep up to a frequency here of 2 megahertz, and this is 500 nanoseconds long, at this point I'll get this first null. In other words, through one channel straight, but through this other channel it's a long length. So now you get just a display that looks exactly like the VSWR display with a short circuit on it, just like this, because two signals are combining. Okay? Now, due to the length of the line, then, this is what you would see when the line is this long. 360 degrees long. First null in the system. Now notice, in this area here, where it's really linear at this crossover point here, this is the slope, the crossing here of this signal. Notice that it's linear only over this small portion of this waveform here. About 30% of this waveform. Now this is a linear plot. I'm going to make this a logarithmic plot in the actual measurement, but keep in mind that the logarithmic plot is still going, so only 30% of this is what we're going to be interested in if we don't make a correction. By that I mean that you're going to calibrate this between here and here, you see, you know how many volts per hertz you would have in the system, because this is the slope of the discriminator. Right? Now if I have a long delay line and I swept out to here, when I get to 2 megahertz, I'd have the first null. How long is the delay line? At this point, 500 nanoseconds. If I keep sweeping, and the line is long enough, when I got here to 4 megahertz, and you divide 4 into 1, of course that decreased it to 250 nanoseconds. But at this point, the time delay in the system is, the time delay is the reciprocal of this. 2 divided into 1 gives you 500 nanoseconds. That means that this line would have been 500 nanoseconds long. Okay? But if you calibrate, this slope here is the only thing that you could use, is knowing the volts per hertz of this discriminator. See, because this is essentially the slope of a discriminator. But in a delay line, that's what it looks like. If you have not measured delay, if you sweep a system like this and you can measure from a frequency here, and you know this is 360 degrees, all you do is say 1 over this frequency and you've got the actual time delay. That's the way it's measured. Well, you can see how that's done here. See, 1 over 200 gives you 500 nanoseconds. That's the time delay. That's starting at 0 frequency and sweeping out to 2 megahertz. When you get the first null, the phase had changed by 360 degrees. So the phase is 360. The frequency is 2 megahertz. And so this is 500 nanoseconds. In other words, the equation is this. That's the equation. Delta phase over delta frequency, where delta frequency is multiplied by 360. Now if you vary this phase so that it's 360 degrees, this disappears, this becomes 1. You have 1 over the change in frequency. 1 over the change in frequency of 2 megahertz is 500 nanoseconds. That's the length of the line. So the differential length of the delay line is where you'll see the first null. The differential length between the two channels. Now you're going to see this in the plots, but I want you to know where in the heck it comes from, because many people usually don't. All right, now we'll look at this in terms of measurement. You saw how it was calibrated. So what we're going to do now is measure the noise power at the Fourier frequency and convert it to the corresponding RMS voltage fluctuation. And remember, we're measuring usually with a spectrum analyzer, you measure in dBm. To do that, you measure the noise power in dBm, make the 2.5 dB correction, divide this by 10, divide by 1,000 to get this into watts, times the resistance to give you the voltage. Once you get that voltage, you multiply it by the calibration factor, and now you have this value that you wanted to know. Now you have to change this to spectral density. How do you do that? You've measured this, and you've measured it in a certain bandwidth, so when you want to know the spectral density, you take the voltage, divide it by the bandwidth, and give you hertz squared per hertz, and that is the spectral density of frequency. So you can see what you're doing. Measure the noise power. This is measured with a spectrum analyzer in dBm. Then you convert this to volts to get this value in voltage. Once you know the voltage that corresponds to the noise power, and you multiply it by the calibration factor, which was what? Volts per hertz. Then you come out with hertz squared per hertz. This then is the spectral density of frequency as measured at the output of that system. You measured the how'd you get this calibration factor? Intentionally modulated. Performed the measurement. You still had to use the same equation up there even back then to get back to voltage. But anyway, you measure the noise power, change it to noise voltage, multiply it to the calibration factor, then divide by the bandwidth, and lo and behold, you get the spectral density of phase, frequency, not phase, spectral density of frequency, hertz squared by hertz. What do you do with this? Take this, you want spectral density of phase. So you take the spectral density of phase, you divide the spectral density of frequency by the Fourier frequency squared, and it gives you radians squared per hertz for the spectral density of phase. What do you do with that value? You normalize this phase to the sideband power spectral density called script L of F. To do that, you just take S delta phi of F, divide by 2 radians squared, in other words, subtract 10 dB, and that gives you the answer. Now this is something that's done in the system downstairs, and so the mathematics you will have. First you calibrate the frequency discriminator, then you measure the voltage and multiply by that factor, and you know now exactly what kind of spectral density you have. Because once you take into account the bandwidth at which you made the measurement, then you know the spectral density. Once you know the spectral density, you can convert that to phase spectral density and then to script L of F, which is the normalized phase noise sideband power spectral density. Then that's plotted. When you plot it, this is what the plot will look like. This is an oscillator. It happens to have noise, it looks like this. Now notice, I told you that it's calibrated only over 30% of that to the first null. Here's the first null at 2 megahertz. Notice, this would have come up here, and if you look this linear, this would have been a null here, and right back down to a null here, as far as, is the distance. But actually, linear-wise, that would have been like this. Do you remember the linear thing that we had for the null? It started at 0 frequency, went up to a maximum like this, and came down to a null. Now this is the same thing, but it's on a log scale, isn't it? But it's still only calibrating that first 30%, which is right here at this Fourier frequency here. So back here, the system is calibrated, and you're measuring phase noise right here. Right on up here. This is minus 110, minus 110, minus 120, minus 130. Here's the noise floor. Look at the noise floor is way down here, isn't it? The noise floor is much lower. Notice something interesting about the noise floor, though. It has a slope, doesn't it? That slope is 1 over f squared, and it gets to be 1 over f cubed in here close to the carrier. But that's essentially what you see in every one of these systems. The only way you improve that and bring this noise level way down is to put a bridge in there or do cross correlation, as we'll show you later. So look what happens here then. This would be 2 megahertz, 4 megahertz, 6, right on out. Every time you have a null in the system. So this delay line is long enough that you go out far enough in Fourier frequency, you see all of this. Now, what happens out here? Just not calibrated. So in our normal first system we used this. If we wanted to measure further out here, we'd get a shorter delay line. See, much shorter delay line. It would take over from here and measure the phase noise on out here. Then we'd get shorter and shorter delay lines to go out as far as we wanted to go. But there is a way of correcting for this, and it'll be shown in a later part here. Now here's a plot to show you, again, how this works. Now here's your first null, see, at about 2 megahertz. Now then you have a delay line here, you see, which has a null way out here. This was, I believe, 600 megahertz here. And you go up to 24. So it was a 6 dB change here in noise. So you went from 600 megahertz, you multiplied up to 2400 megahertz, and this is a plot you would get. Now you see, 20 times the log of that ratio is the 6 dB that you see here. So you multiplied 600 megahertz up to 2400 megahertz, you got a 6 dB increase in the level here, 20 times the log of n. And n was 4 in that case. Now here you can see it's calibrated up to here, but notice this one, we put a shorter delay line, we went way out here. First null came in way out here. So you put two different delay lines and measured this, but you got the same phase noise here, and all you do is correct this by 20 log of n, and these two are exactly the same. And that shows you the phase noise system was working with 2 different delay line lengths at 2 different frequencies altogether. One was 400 megahertz, as I said, the other was 600, and the other was 24. Now here's what happens, or this is what you have to do. Correct. Here's it's normally calibrated, see, for this portion like here. Now to correct for this is sine squared of omega tau, where tau is the delay line length out here. In other words, a particular Fourier frequency you're measuring at. It has a reverse, reciprocal, that's the time delay. So the time delay divided by 2. If you make that correction there, then you can see your null is going to come in over here. If you make a correction, it'll just plot right on out here and you'll get the true phase noise. The reason you get this spike here is because when you went down to this point here and made the measurement, the spectrum analyzer went down below where the spectrum analyzer could measure. So you got a discontinuous measurement at this point because this goes down where the spectrum analyzer just cannot measure. So you got a big spike output here. So in this area, it's not measurable. So the only thing you do is in your system, you'd correct it and say, if this goes below a certain value, ignore that reading, then it would just plot right straight on through and you get the phase noise. So then, even though you go beyond the point where you originally calibrated, it's still calibrated. It's calibrated because you correct for that variation. The correction is this equation here. So Fred did this in the system, and here, instead of the phase noise coming here and looking like a dip in the system, which is, in other words, uncalibrated from this point on down to here, he made the correction, and you can see it just went right out here and plotted true phase noise of that device. So that's another contribution by Fred. With these systems, you notice you can see everything in here. You can see radio stations, everything else that exists in here. And of course, in this particular building, you can imagine what we found. We found a lot of frequencies in there that people get very disturbed when you mention that kind of thing. All right, to talk about the noise floor. In order to measure in close to the carrier, you see, you have to have a long delay line because you have to decorrelate the signal. And the lower the signal gets, the longer this line would have to be to decorrelate it going in close to here. Now you see that as short of the delay line, look what happens. The noise level goes up. The noise floor changes. So what Fred did, he put a bridge across that. And this is the 2 oscillator right here, noise floor. You see, it's a big difference. But this is that 1 over f squared slope that I told you have with all delay line discriminators. That's a noise floor slope. So if you put this RF bridge in, he just lowers this by 20, 30, 40, 50, 60, 70 dB. Now here is what they call a dual autocorrelator again, where you feed the signal into to a mixer on one side and another mixer and then do a cross correlation. That's the same thing that we showed you before. Now that's another way of getting a better noise floor. Do a cross correlation, you get a better and lower noise floor. Here's the way we got it. This was Don Halford's idea. He put in one of his notebooks he'd like to see a dual delay line discriminator and do the cross correlation. So I made a big circle around that in his notebook, and I said, Wendell, the first time we can do it, let's do it. So Wendell built these 2 up, this one and this one, fed them through and into a dual fast Fourier analyzer here. It's a digital signal analyzer, but it's a 2-channel. And he did a cross correlation. In other words, cross spectrum measurements on these 2. And he picked up about 20 dB of sensitivity in the noise floor, just using a dual system like this. Picked up somewhere around 20, 22 dB of sensitivity as far as the noise floor is concerned. So then again, that made it possible to measure with a delay line discriminator. You could measure very much lower noise single sources because you had a lower noise floor. That's one way of doing it. It's the same delay line discriminator, but you go through 2 channels, calibrate 2 channels, do the whole bit. But you have a noise improvement of the noise floor, and you can measure with a sensitivity of 20 or 22 dB later. Now Fred LeBar got rid of all that by this simple scheme here. Here's his normal phase shifter for 90 degrees. This is the delay line and into here. But what he did here, he took a phase shifter and attenuator across the delay line, and he tuned these so that he nulled out the carrier completely at the output here. Then he had, if he lowered the carrier by, say, an extra 40 dB here, he put an extra 40 dB gain in an amplifier here, amplifying the noise up. Now you've gained all kinds of sensitivity. You've gained 40 dB of sensitivity by putting in this 40 dB amplifier. And that's the way he did it. The higher the gain of this amplifier and the more you tune this out, you can get up 50, 60, 70 dB of sensitivity more. And that really improved our our single oscillator measurement capability. Made it so that you can measure single sources that no matter how good they are. Whereas previously you were really limited. So here's the delay line, the variable attenuator, and the phase shifter. This is the math that you go through to show this. This is the transfer function here. So it's calibrated in this area here. Then when you apply this correction here, that means that you no longer have the, you no longer have that nulls in the system. You correct for them. So this was a great contribution to our system. And it was very important in some other measurements. Here's what it looks like then. Delay line, bridge, and the bridge, phase shifter for setting quadrature, low noise amplifier here. So this amplifier, you see, increases the sensitivity considerably. Even without that, you increase the sensitivity. You can do better by getting rid of the carrier like this. Well, this amplifier, it would really improve the system. This is a plot that Fred made of the various transfer functions. This is the two oscillator technique here. There's just two oscillator method. Then you have the classical delay line discriminator, which is number 2. That's this one here. Then he get number 3 here, was with the delay line bridge. So he's really improved the system considerably, much more sensitive. Here's one that's very important from the standpoint of a system. Suppose you have a system now that you want to calibrate, you want to deliberately FM that signal to get a calibration. Well, it turns out when you have millimeter sources, you can't do that. This source here, if it's very, very noisy, you can't FM it and do a proper calibration. So what you do, you take this and use AM modulation and set up your power levels and so forth here with this source for calibration, and you calibrate this system in terms of AM to get the FM modulation index. So you get the modulation index by AM modulating the signal to get what you want here is for the FM. I've given you an illustration of that in the paper, so I'm not going to go through that. But once you do that, and that's specifically the only reason for this, is you have a very noisy source. You use AM modulation to obtain the modulation index. Then, of course, the calibration is the same. The DC oscilloscope to look at this and make sure that you can maintain phase quadrature and that you can note this and observe it and make sure that it remains there. The rest of this is straightforward, the same system we've been using. Now, in case you want to know what this looks like you saw the cable before, the big round cable for delaying the signal. Many, many rings of that black cable on the bench. This is at 94 gigahertz. Notice this delay line is only this long here. Now this one, this long one here, you see, is so you can get in close to the carrier. Then when you're going out further from the carrier, you can put in these shorter delay lines here. So then you'd have a calibration in close to the carrier down, say, like this. I'll say, like, you have down to this point. Then you change cables and you go down here. Then you change another cable and going down here. So you change these from the long one to get in close to the carrier to this one out from the carrier, this last one here to get out from the carrier down here. So as you go out in Fourier frequencies, you shorten the cable so that you can measure farther out. Now, the reason we did that, of course, we didn't have that correction that Fred was using in the system. Okay. The reason this can be done like this with a waveguide, as you know, you're worried about the delay, the time delay, and the reciprocal of the Fourier frequency giving you the value of time delay. You know that a waveguide is dispersive. However, over this narrow band of frequencies that we're dealing with here, even though it's dispersive, it's not interfering with the actual measurement as far as the decorrelation and the actual calculation of phase noise. But that's what the system looks like for measuring here. And of course here, this is your mixer. So here's a delay line RF bridge. In this case, this delay line up here is just a little coil of waveguides. You guys go in the lab next door, in the engineering lab, and you'll see that this is just a little circular thing of waveguide all wrapped up in a coil through this isolator. So anyway, the bridge is built up. If you guys like to see it, you can go next door and see what it looks like. It's a very unique little unit. This is a curve that just shows you some of the work that Fred did on some very high frequency sources. And what he was doing here is checking the loop bandwidth of some phase locking systems that he was using in here. He did a whole lot of measurements, and I don't know, he had an 8-foot length of WR10 waveguide, and he was doing some special measurements on here on he had an 8662 here, and he did some klystrons and other values, other units, just to see what kind of phase noise he got. You can look at those in the book if we still have some of those pictures in there. One thing he did, though, he took a good oscillator with the best oscillating characteristics, best phase noise characteristics he could get, and multiplied it up, and he verified the fact that he multiplied this up and he didn't get any increase in noise by multiplying it up. Taking into account 20 times the log of n, he got the true value of the multiplied noise, and he didn't have an error. All right, let's just go ahead and take a quick look at this then. Attenuator, pattern, isolator, attenuator, pattern, isolator. Now, when you are going to make measurements, notice what this says: amplitude noise measurements. For amplitude noise measurements, you cannot use a delay line. Both sides of this line must be the same length. Same length. This length and this length have to be the same. Signals going in here. In this case, of course, you tune the signals to be in phase, or 180 hours of phase, and to perform the measurement then, and you minimize the difference. You minimize the differential delay between the two ports of the local oscillator. And this is the way it's done. A power splitter up to this side here. The measurement technique then, as far as the basic measurement, essentially the same. Calibrate the output of the mixer by doing this, measuring the same way we did before. The equations, of course, are for AM modulation instead of FM. One thing I wanted to show you here. Here's the phase noise of a device. Here's the AM noise. When you look at devices, oscillators and synthesizers and so forth, the FM noise is the predominant noise. This is the AM noise. Many times there are people out in the area who've made measurements. They're trying to measure this, and they're usually measuring some part of this. You see, AM noise is always so far below FM noise that the predominant noise is the FM noise. And you're trying to make these measurements and use a basic mixer. It doesn't have enough isolation. You're going to measure some of this if you're not careful. And it's also, suppose you have a system that has some AM to PM conversion. Then that FM is going to be converted, and you'll get an AM component here. These measurements all interfere with. Here again is your phase noise, and here's your AM noise. AM noise usually, remember, is not the problem. The FM noise is the problem. Now here's that, remember I mentioned previously that we had an oscillator that we measured in different systems, and we got different phase responses. Now this is there was a SAW oscillator, surface acoustic wave oscillator. Here's the phase noise. This phase noise should have kept going right on up like this, you see. But yet our measurement tailed off like this. And the problem was that we were using two of these SAW oscillators. I mean, using this, these two SAW oscillators, and they were injection locking to each other. In other words, there was not enough attenuation between the two, and even just sitting out here like in space, they just injection locking through there and through the the cabling of the system. So it was injection locking, and what happened? This looks like a phase lock loop in here, and decreased the phase. Normally, though, this should have gone straight on up. In another system, that's exactly what happened. We measured the phase noise, and it goes right on up to 0 at the carrier. And right here, you see, we had injection locking of the two oscillators. That's another thing you have to worry about in a two oscillator technique. One thing that you find here at TRW is that we're very consistent in the fact that we like to make measurements using the delay line technique. Because you only have to have one source, right? That's fine. But suppose you have a case where you want to use a delay line discriminator, and you have two sources at some very high frequency. See, once you have this good baseband, low frequency measurement system with a delay line discriminator, it's very easy to take two sources. This is millimeter sources. I think this is up around 40 gigahertz. Or 34 or something like that. So you offset those by 2 gigahertz and use the delay line discriminator. In other words, down to S-band. And that's exactly what we do here a lot. We take two sources, beat them together, get the difference frequency, and measure the phase noise in our regular single oscillator phase noise measurement system. It's a very good technique. Now, we've done that a lot here, and like I say, the reason is this is a simplified system. It's pretty hard to get all those systems built at all those. You saw that millimeter delay line, right? That gets to be a problem building all those waveguide delay lines. Whereas you just beat that down to the low frequency and do the whole damn thing in a coax system. Here's a phase noise, again, an AM noise. Now there is a real problem to make some measurements like that. And as I say, there are frequently very serious errors in measurement of this because they get portions of this phase noise in here because they don't have adequate isolation, or they don't have the system tuned properly, or they just plain don't know how to make the measurements. Now this is the Hewlett-Packard system using a delay line, and they again have their delay line going into the mixer, and they probably have their phase lock. And this goes out to the spectrum analyzer. I don't know where they have their phase lock loop in this thing. They don't have any here, but I thought if they had the one where they go into a second oscillator, they might have something like that. But here they're generating this frequency coming in here, and it goes through the delay line and in here. So it's just like the one we looked at before. They did have usually a second oscillator, when they beat two oscillators together to get this frequency down to the delay line frequency the same way we did before. But they don't show that here. I guess, yeah, they could do it here. You have one under test, so you beat this together here and get it down to the low frequency of the delay line and use it. So again, it's the same technique I showed you before. You beat this one against their particular comb frequency here, get the difference, and now you're down at the delay line frequency, and you can make everything down here. They make all the measurements with a delay line discriminator. That's the same diagram that I showed you before, and all they're showing here is the various comparison of system sensitivity for various. The 3047, which is an HP system. This is an HP system. All of these, the 5390 here is a time domain type of measurement system, which will measure way down, very close to the carrier. But it's a time domain, which means you take a counter and you measure the zero crossings of sets of measurements, over a period of time. You make a set of measurements with the counter, another set of measurements, another set of measurements, and then you calculate in the time domain, you calculate this spectral density. Delay line, RF bridge, discriminator, noise floor, all of this is worked out mathematically by Fred LeBar to show you how far down this noise floor is. Now, in the case that he worked out, he actually came up with measurements, being very careful. He could tune out a bridge and get an increase in sensitivity as much as 70 dB. And that is really, quite a feat. This other work here has to do with pulse phase noise, and I do not intend to get in there. Again, here's a picture of all of our system put together so we could make measurements over wide frequency ranges and so forth, where you have all of your instrumentation. And you had various amplifiers, power supplies to run everything, and you had your calculators and plotter. So the whole system was set together originally to look something like this. Hewlett-Packard built a system, and they condensed all of that down to a system that looks like this. This is the Hewlett-Packard system. We have one of these in the engineering lab. You guys are free to come in and take a look at it, and maybe get Floyd or Neil to give you a practical orientation on it. Certainly, if you ever make measurements down in the lab, that's what you're going to do. Now, I think that the last week's lecture on spectrum analysis, where we showed the actual calculations, how you calculate and make corrections to get the proper measurements of power with a spectrum analyzer, I think it was very complete. And I think that you should have picked up a lot of ideas now about this relationship of noise figure of spectrum analyzers, how to improve it by an amplifier, and now you know exactly how to check it out so quick that you don't have to ask anybody. Just go ahead and measure the noise levels, convert them with all the corrections to a 1 hertz bandwidth, and compare that to the minus 174, which is the thermal noise level. Then you know more about that system, and you know exactly how good you can make measurements with it. Now, when you incorporate that in the phase noise system, the only thing that's important is you know how the phase noise measurements are performed. I think you've seen here the important point in the type of measurements we make with this particular phase noise measurement system we have here is that you suppress the carrier, and now you can measure way down. A direct measurement with a spectrum analyzer, we found it was very limited. And I hope that this has given you some idea about phase noise. If you ever have to do the measurements, you have a very good set of papers to go by. You have very good instructions. Also, you have an automated program in the system that we use here at TRW, and I think that's sufficient to get you to the point of performing very good measurements of phase noise. But remember, there are no standards for phase noise. The inaccuracies and everything that I showed you that were calculated for the single oscillator system and the two oscillator system here at TRW are strictly based upon the characteristics of all of the instrumentation that's used, and including the technique. So I believe that that's sufficient as far as phase noise is concerned. So I'd like to close the lecture at this point. In the future, if you want to look at these tapes and see if they're any good, feel free to do so. What I'd like you to do is, everyone have that phase noise paper?